Now let's look at the integral of sine to the m times cosine to the n, where both powers are even. In this case, neither of our previous substitutions are going to work because we can't split away that extra cosine or sine to act as the derivative du, and at the same time be able to convert everything else to either sines or cosines. So if both powers are even, one thing we can do is reduce the powers using our half-angle formulas from pre-calculus or trigonometry. We have sine squared of x is 1/2 times 1 minus cosine 2x, and cosine squared of x is 1/2 times 1 plus cosine 2x. Alternatively, you can switch to powers of sine and cosine using cosine squared is 1 minus sine squared and vice versa, and then use the reduction formulas which we talked about a little bit in the previous section, and we'll look at that later. Let's try the half-angle formulas on the integral of sine squared x times cosine squared x dx. Now, if we convert sine squared and cosine squared using these half-angle formulas, we end up with the integral of 1/2 times 1 minus cosine 2x times 1/2 1 plus cosine 2x. And pulling out those 1/2s, we get 1/4 times the integral of something of the form 1 minus a by 1 plus a, which is equal to 1 minus a squared. So we end up with 1/4 of the integral of 1 minus cosine squared 2x dx. Now we can actually use the half-angle formula again for cosine 2x. This time the angle is 2x, theta is 2x, and this is equal to 1/2 1 plus cosine 2 theta, which is 1 plus cosine 4x. So replacing cosine squared of 2x by 1/2 1 plus cosine 4x, we get our integral, the integral of sine squared cosine squared, is 1/4 times the integral of 1 minus 1/2 times 1 plus cosine 4x dx. Tidying that up a little bit, we're looking at 1/4 of the integral of 1/2 minus 1/2 cosine 4x, which is 1/8, times the integral of 1 minus cosine 4x, and this is pretty simple. The integral of 1 is x, and the integral of 4x, of cosine 4x is sine 4x over 4. And in all, we end up with our integral, the integral of sine squared times cosine squared is x over 8 minus sine 4x over 32 plus a constant. Now you also have some extra examples in your notes which you'll probably see on some quizzes, and in these cases you can use these half-angle formulas when you're working through them. If both powers are even, there's an alternative to using this half-angle formula. You could switch to powers of sine and cosine by converting cosine squared to 1 minus sine squared, or vice versa. And then the reduction formulas, which you can derive using integration by parts, look like the following. The integral of cosine to the nx can always be written as some function plus some constant times the integral of cosine to the n minus 2. So you reduce that power by 2 steps, and then you can apply the formula again to the integral of cosine to the n minus 2 to take the power down by 2 more steps, until you get to something like the integral of cosine squared or the integral of cosine, which you can integrate using very simple methods. Of course, for the integral of cosine squared, you can use the half-angle formula, and you can do the same with any power of sine. So, for example, if we're looking at sine squared times cosine squared, I could convert this completely to powers of cosine by switching the sine squared to 1 minus cosine squared. And if I replace sine squared by 1 minus cosine squared, this integral is the integral of cosine squared x minus cosine to the 4x dx. Now I could write the integral of cosine to the 4x dx as some function plus some constant times the integral of cosine squared x dx. And of course, cosine squared of x, I can just solve that using the half-angle formula. So I can solve this using a combination of these reduction formulas and the half-angle formula.